Okay friends, welcome back. So in the previous video, we deployed Nutanix Kubernetes Platform with GPUs in an internet connected environment. This time round, what we're going to be doing is we're going to be deploying Nutanix Kubernetes Platform in an air-gapped environment with GPU capabilities as well. So let's dive right in. So over in the blog, I have documented the steps to deploy Nutanix Kubernetes Platform in an air-gapped environment. The first thing that we want to do is we want to download the air-gap bundle. I have it already downloaded in my internet connected jump host. So we will need to download a couple of things. The first one is the NKP Air Gap Bundle. The second one is the Ubuntu 22.04 Debian packages. So the Nutanix image builder for Cluster API will use this particular Debian package bundle to build the Cluster API compatible image. If you're using GPUs, which in this video we will be, we need to download the Ubuntu 22.04 build packages as well as the NVIDIA driver run file. So I won't cover how to download the NKP Air Gap bundle. Is all documented here. We just need to run this command with the URL that we get from this link, and then we can extract the bundle, right? So it's already extracted over here, but if we want, we can just run it again. So now that the bundle has been decompressed, the thing that we're interested in is the CLI command. So cd CLI and copy the NKP binary over into user/bin. So once that is done, then we can hit back into the block and we can run this command so that it prepares the Ubuntu 22.04 Debian package bundle. So now that is done, we now have an artifact that contains all the Debian packages that is required to make an image Cluster API compatible. So the next step would be for GPUs only. So if you're doing, if you're going to be using GPUs, then we can run these commands. This uses Docker to download build essentials, GCC 12 and G++ 12, as well as make, so that we can perform an installation of the NVIDIA GPU driver. So we're going to be using GPUs here. So let's run this command. And once the download is complete, we have a new artifact called, or rather a new directory called Ubuntu 22.04 build packages. We can then tar and compress this folder. And this will be the third package that we will need to copy over. And the last one will be the NVIDIA GPU driver, right? So we can head over into the Nutanix portal. We can check which edition of the GPU operator NKP ships. So at this current point of time, NKP 215 ships with 25.3.0. But I'll show you where to take a look at that. So we can head over into the documentation, software documentation, Nutanix Kubernetes Platform, select the version that you are currently installing, and select the release notes. Then we can search for NVIDIA, and this will show us the version of the GPU operator we're going to be installing. So it ships with 25.3.0. What we can then do is go to the release notes, click on it, and the release notes tells us what's the version of the GPU driver that we need, right? So it's 25.3.0 under the release notes, and it tells us that, okay, we should download and use the default recommended version of 570.172.08. So we can just search for Google, and this gives us the download link over here. So we can just right click, copy link address, head over into our terminal, and just wget. So we now have got the four key files that we're interested in: the Debian package bundle, the NVIDIA GPU driver, if you're using NVIDIA GPUs, the NKP Air Gap bundle, as well as the Ubuntu 22.04 build packages. And this is if you're using GPUs only. So what we can do now is we can transfer all of these images over into the Air Gap jump host. So I've now copied all the files into my Air Gap jump host. I can see that the jump host is prefixed with AG, which is air gapped, and the files are here. If I ping 8.8.8.8, it's not available. Ping 1.1.1.1, not available as well. Okay, so now that we've copied everything over, that's the last time we're going to be using the internet connected jump host. Everything else from now on is going to be running from the Air Gap network. So if we head over into the block, we can create the base OS virtual machine. So we're going to be using this virtual machine to be creating a Cluster API compatible image for us to deploy Nutanix Kubernetes Platform with. So we can do that. Head over into Prism Central, create a new virtual machine. I'll call this Ubuntu 22.04 image AG, which stands for air gap, management cluster, some CPU and memory. I'll clone CD-ROM, and I'll attach a 80 GB drive. So why 80 gigs? Well, the default installation of Nutanix Kubernetes Platform deploys the worker nodes and control plane nodes with a disk size of 80 gigabytes if you don't specify anything else. So if we were to create a image that is more than 80 gigabytes, it's going to fail, right? Because we're trying to create a image, or rather a virtual machine with a drive that is sized smaller than the original image itself. So we can create with 80 GB first, and I've got a script that automatically resizes the partitions when we provide it with additional space. So we'll take a look at that later on. I'll attach it to a subnet, and it's going to be the air gap subnet, and create the virtual machine. So after the VM is created, we can power it on, and I will proceed with the installation steps. So I will pause at the partition layout so that we can create a CIS recommended partition layout as well. So as we can see, we are trying to install in an air-gapped environment. The mirrors will time out, and that's because we cannot access the internet from this network. So I'll just go ahead and skip this mirror checks. So here is the partition layout. I'll just configure a custom storage layout, and I'll create a GPT partition that is going to be mounted as boot, and I'll just use 1 GB, and I'll use the rest as an LVM. And we can then create the necessary partitions that is recommended by CIS. So we have created the recommended CIS partition layouts. The sizes will differ based on customer environments, but this layout is very common in security-focused customers. So let's go ahead and carry on with installation. So now the VM has completed its installation and completed its first boot process. We can go ahead and log into that virtual machine. H12. So let's first edit the FS tab so that we can implement the CIS recommendations. And now that is done, we can use the script so that we will automatically resize our partitions when we give it additional disk space. So we need to make sure that our partitions are named correctly as well. So if we check our lsblk, we see lvvar. Lvvar is for var, that's correct. lvroot is for root. lvvarlog, lvvarlog, and lvvar log audit. Looks good. So this script, what it does is that it will detect if there are additional space that is allocated onto the virtual disk. And if there is, what it's going to do is going to extend the logical volumes based on the amount of percentages that we have over here. So you can feel free to just make the changes if necessary. If you do not want to expand var log and var log audit, you can remove that as well and just change the percentages over here. Now this unit runs once only. So if that is this marker over here, what it's going to do is going to detect it and not expand the volumes anymore. So once that is done, we can run this generalization commands to generalize the virtual machines and prepare it for the next step, which is to create a cluster API compatible image. Now I'm not going to do that yet. I'm going to clone this virtual machine so that I can create a GPU compatible one as well. So I'll just click on clone, accept the defaults, and create. Then I can edit the GPUs and attach a GPU to it. Then power on this VM and wait for it to boot up. So while that is booting, we can go ahead and complete the non-GPU air-gapped image. So we can head back to the block and just run these commands. Then we'll clean up the system, then power off. Then over in Prism Central, I can create a image out of this air-gapped image that we just built. So I head over to my images tab, add the image, select the VMDs, and I'll select the image-ag, remove the suffix, and create. Then now we can test that the virtual machine is working as expected. So I'll just call this resize test ag, management cluster, some resources, and I'll clone the image from the ag image that we have. I'll give it 200 gigs to test that the resize works. Attach it to the air gap subnet, and use cloud init to ensure that my cloud init is working as expected. And I can power it on. We wait for it to boot up, and then we can SSH into it. So now the VM has booted up, get SSH. And if it works as expected, we shouldn't need to key in a password. Great. Then if we lsblk, we see that the partition has automatically resized. Looks good. So we can delete that virtual machine. So now we can work on the Node OS virtual machine with the GPUs attached. So the first thing that we need to do is we need to copy the NVIDIA driver run file as well as the build packages. So we can SCP the packages into the virtual machine. Then SSH into it. So we now see that the packages has been copied into the virtual machine. I am going to decompress the build packages. Then we can go back to the blog and find that commands to run so that you automatically install everything for me. Then we can update the alternatives. Great. So once that is done, the next step will be to blacklist no view. Right, so it's there's a installation guide from the NVIDIA documentation, and it's asking us to blacklist the no view kernel module. So we'll do that. And then update the init ramfs. So once that is done, we'll go ahead and reboot the VM first so that the changes will take effect. And once the VM is back online, we can SSH into it and check that the module is no longer loaded. Great. So once that is done, we can then install the NVIDIA GPU drivers. So if you are using, I have the CIS recommended partitions and mount options, so I need the temp directory /opt. But if you're not, then you don't have to do that. I'll just use the NVIDIA proprietary kernel modules, and I'll continue the installation. So now that the installation is complete, we can run a command to check that the GPU is available, right? So we can just run the NVIDIA SMI command. So now we can see the GPUs. The installation has completed successfully. The last step would be to generalize the virtual machine and pack it up for use with our Nutanix image builder. And we can power off the VM. So after the VM is powered off, we can head over into Prism Central. Wait for the VM to be powered off. And then we can head into the Images tab. Create a new image from a virtual machine. And I'll select the air gap GPU that we just created. And remove the suffix. And click on Next and Save. Now we can test that the image is working as expected. So first we create a virtual machine. Let us call this GPU resize test. Management cluster, some resources, attach a disk and clone it from the image that we just created. So the image air gap GPU, I'll give it 200 gigs so that we can test the auto resize. Attach it to the air gap subnet, attach pass-through GPU, and use cloud init to test cloud init is working. And create a VM. So VM is now created, you can power it on. And we can SSH into the VM. So if it works, we do not need to key in any password. Good. Let's take a look at our directory sizes. So it's all been resized properly. And let's check our GPU. Good. So we know the image is working as expected. We can delete the virtual machine away. And the next step will be to create cluster API compatible images using the Nutanix image builder for both the non-GPU and GPU image. So the next step would be to create a cluster API compatible image from our base OS that we created earlier. So we'll be doing this for the non-GPU one. When we are running Docker commands, we need to run it with a sudo. So let's make some configuration changes so that we don't need to use sudo in order to run Docker. Right, so if we run this command now, we should be able to see no errors. So the next step will be to extract the NKP air gap bundle on our local machine. Now that it's extract, we want to copy the NKP CLI into the /user/bin directory. And then we can check that the CLI is working as expected. Great, so we have got the NKP CLI installed. The next step will be to load a couple of images into Docker. Docker load -i convoy bootstrap image. and the NKP image builder image. So now that the images has been loaded, the next step that we need to do is we need to copy the Debian package bundle over into the KRB artifacts directory within the nkp v2.15.0 folder. So we can copy that in, and if we ls, we see that the package bundle is here. Then we can export a couple of environment variables. I've already exported my Nutanix user and password, so I'll skip that. I'll just export the PC, FQDN, and PE cluster. So this one is your IP address or FQDN of Prism Central. Then Prism Element cluster where we want to run the build process on. The subnet where we want to connect the virtual machine to. So we'll choose the air gap subnet. And the source image, which is the non-GPU image that we created earlier. And the disk size is 80 gigs, as well as the remote folder being /home/ubuntu, because I have CIS recommended partition layouts and mount options. Then once that is done, then we can go ahead and run the command. So now the build has completed. We see the artifact has been generated. So if we take a look at this in the Prism Central Images folder, we see that the image has now been created. So we can use this image to build Nutanix Kubernetes Platform clusters without GPUs. So in this section, we'll be creating a cluster API compatible image from the base OS with GPUs that we created early on. So I've already exported my Nutanix user and Nutanix password for Prism Central. I'll just export the rest of the environment variables. So the PC IP FQDN, this is your IP address or FQDN of Prism Central. Then the PE cluster is the cluster that we want to build, to run the build on. Subnet that we want to attach the virtual machine to. So we'll use the air gap subnet. The source image name, this will be the GPU capable image that we created earlier. Disk size is 80 gigs, and the remote folder, because it is CIS recommended partition layouts and mount options, we will be using /home/ubuntu. Then once that is done, we can go ahead and execute the command. So the build process has completed, and we see an artifact was getting generated. So it's this artifact over here, and we head over into Prism Central and refresh. You can see that the GPU artifacts here. So we can use this image to deploy NKP cluster with GPU capabilities. So in this section, we will be populating our air gap registry with the Nutanix Kubernetes Platform container images. So if you don't already have a Harbor registry, you can just follow this guide over here, and it's going to show you the steps on how to deploy Harbor in an internet connected or air gap environment. So I've got my Harbor page open here. I'm just going to log in. Then I'll create a new project and call this mirror. So this is where I'm going to be storing all my NKP container images. Then we can export some of the environment variables. Head over my jump host, and my NKP folder is nkp v2.15.0. So I'll just use the same naming syntax. The instructions are here. The registry mirror URL. So this is the registry mirror, the registry that I'm going to be using, that has got all the container images. So make sure you put in the /mirror as well. So it's a project we just created in Harbor earlier. The username and the password. As well as the CA chain for Harbor. Just validate that we can access it. Great. So then we can run these commands, and it will automatically populate the registry for us. So now our container images has been successfully pushed into the Air Gap Harbor registry. The next step will be to deploy Nutanix Kubernetes Platform. So in this section, we will go ahead and create the Nutanix Kubernetes Platform cluster. So we've got environment variables to edit. So let's get started. Click on the copy button over here. Head over into our jump host. Then we can use the VI editor to edit the environment variables. Okay, so cluster name, this will be WSKN AG NKP management. The control plane IP address, this will be 10.168.104 and 30. The image name, this will be the cluster API compatible image name that we created earlier. So this one. So I'm not going to use the GPU one yet. That will be for our workload cluster. The Prism element cluster name, this will be the cluster that we're going to be deploying the cluster on. So it's going to be management cluster. And the subnet will be the air gap subnet. I'll leave the control plane replicas and configuration as it is. The storage container name, I'm going to use the default self-service container. But you're free to choose whatever you want to use. So under storage containers, there's a self-service container over here, but you can use anything else that you feel comfortable with. Then the load balancing start IP. So this will be the IP address of the ingress controller. So the first IP address will be the IP address of your ingress controller. And the ending IP, anything in between the first IP address and the ending IP address will be used for additional load balancer services that you might request. The SSH public key file, so let's validate that we have one. Okay. Let's copy that. The PCFQDN with port. So this one, if you are using an IP address, you would just key in the IP address like that, right? But if you are using an FQDN, make sure that the FQDN is within your DNS entries. If you're using an IP address, also you got to make sure that you use the -- insecure flag. And for the Prism Central certificates, I will get the certificate path. We can just leave this alone. The Prism Central user and password I've already exported, so I don't have to do that. Container registry. So this will be the registry whereby you are hosting all your personal container images, right? So this is AG registry.wsk.local. You don't have to put in the suffix or the project name over there. The username will be the defaults. This will be changed later on. The registry CA will be a standard CA that we're using. And this is where the NKP images are hosted. The registry username and password is the defaults. CA chain will be the standard one. And this is where our ingress will come in. Right, so I'll just be calling this WSKN AG NKP mgmt.wskn.local. So this is going to be the FQDN that I can use to access Commander. The ingress cert will be server.cert. Key will be server.key. And the CA chain will be the standard CA chain that we have. Done. So the next step will be to run the command to perform the installation. Right. Everything here does references the environment variables that we created earlier, and it does loads the environment variables from the env.sh file. And we've got the --air gap installation flag as well. So this takes about 15 minutes. I'll just speed up the video here. And when the cluster is up, then I will open a second terminal for us to see what's happening under the hood. So if we head over in the Prism Central, we should see that the first virtual machine gets spun up. There we go. So in a couple more moments, we'll start to see more virtual machines get spun up. So here we see that the 4 worker nodes have spun up and spinning up the second control plane node. So once we see this initializing new Capi components, we can open a new terminal session, and if we were to go into where the directory which we executed the installation from, we'll see that there is a kubeconfig file for the cluster that was just created. So we can export kubeconfig equals to the directory and the kubeconfig file, and we can launch K9S to take a look at what's happening under the hood. So now we see NKP has successfully been installed. You can get the dashboard details. Use this URL. And I'll head into my airgap jump host. Log in using the provided username and password. And there we have NKP 2.15 installed in the airgap environment. So let's upgrade the licenses so that we can deploy a workload cluster. So after applying the licenses, I refresh the page. You see that I have now been upgraded to NKP Ultimate. So the next step will be to create a workspace. Head over into the clusters page. Click on Add Cluster and Create Cluster. I'll call this WSKN AG NKP GPU. Username, I'll leave it as Convoy, and I'll select the public key that I have. I'll configure the node pools into the management cluster. Select the airgap subnet, and I'll give it a control plane IP address. I'll leave it as the defaults. Select the self-service container and the IP address for the load balancing range. The registry mirror will be the registry mirror where I keep all my NKP images. And the CAcert. And the same for my private registry. Then we can go ahead and click on create. So once the creation process has started, when it hits the provisioning, we can add on an additional node pool that will allow us to add on the GPU nodes. I'll select the GPU image, pass through GPUs, and select 2 replicas for my workers. Give it 16 CPUs and maybe 64 gigs of RAM and 200 gigs of disk space. So the provisioning process takes a while. We can head into Prism Central and we should see the GPU nodes coming up. There we go. This is the first one. So let's just wait for the provisioning to complete. So if we head back into Prism Central, we should see that the worker nodes are starting to come online already. And we see that there are 2 GPUs in this particular worker node, GPU 1, GPU 2, just like we requested in our NKP cluster. So it seems like all the nodes have been successfully provisioned. We're waiting for the last control plane, after which we can download the kubeconfig of the cluster. So now we see that the cluster is ready. We can go ahead and download the kubeconfig. I'll just paste this over into my jump host and export the kubeconfig. Then we can launch K9S and take a look at what's happening inside. So we see that things are still getting deployed. But what we can do is we can go ahead and enable the GPU operator. So over in the Applications tab, we can search for NVIDIA. Click on Enable. Select the cluster and enable it. Then in a couple of moments, the NVIDIA GPU operator will get deployed in the cluster. So now we see that the GPU operator has successfully deployed. If you were to take a look at the CUDA validator, which is a simple app that NVIDIA has to validate that the GPUs are working as expected, we see them both running for both the nodes. If we take a look at the nodes and look at our worker nodes with GPUs, we see that we do indeed have the GPUs properly labeled. GPU count equals to 2, GPU.product is NVIDIA L40, GPU memory, that looks good. And we can also head over into the Kubernetes cluster under Grafana. Get the username and password. And head into the NVIDIA GPU DCGM exporter. We can see our GPUs as well. Alright, that concludes this video. Thanks for watching, and I'll see you in the next one.